Hi, everyone. First, especially when any of we have the information shared today to help increase equity and help human beings register for today's event. Remember, you can submit after our NASA experts talk. Today, we are joined by the NASA Mars Curiosity Project scientist, Dr. Ashwin Vasavada. Ashwin will give us an update on the Curiosity mission that has been on Mars since 2012. Ashwin?
Hi. Should I take it away?
Yep.
Okay, great. Hi, everyone. I'm Ashwin Vasavada. I'm the project scientist, as Ona mentioned, for the Curiosity Mars rover. And the Curiosity rover, of course, has been on Mars since about 2012. So we're almost at 8 years. This August, it'll be 8 years of exploration on the surface of Mars. And so I'd like to just go over for the next 25 minutes or so where the mission's been, what we've been finding, and talk a little bit about what lies ahead, and hopefully get you all caught up to date on this incredible mission and everything that we're discovering about Mars. So I believe we're looking at the title slide, or we soon will be. And the title slide of the talk here just shows a self-portrait that we can take with the rover. You may be wondering how we get pictures like this. And some of you probably know that our clever camera folks invented a trick a few years ago, along with the engineers at JPL, to actually use the robotic arm of the rover to take to use the camera at the end of the robotic arm to take pictures of the rover itself. Now, unlike your cell phone camera, which is a very wide field of view, the camera on the end of the arm was designed to look at rocks very close up and with a very narrow field of view. So we actually have to stitch together over 50 different pictures to create this one selfie that you're looking at now. But nevertheless, it's great that it works, and it gives us this wonderful view, just like you're right on Mars with the rover. And what you're looking at here is a drill hole that we drilled a few months ago. And you can see the hole in the rock just to the left of the rover. And that's what this rover is all about, drilling rocks, gathering the material from the rock, and analyzing them to learn about Mars. So let's dive in. I do want to mention on the second slide, slide 2, just to acknowledge the fact that things are different for us, like so many people around the world. The Jet Propulsion Laboratory has also been exercising a lot of caution with its employees. So many of us, most of us, in fact, have been at home for the past few months. And we've been inventing new ways of operating Curiosity to accommodate for that situation. And we're very pleased and very thrilled, in fact, that we could continue to do our jobs from home, even operating this very complex machine. So it's wonderful to be able to still do that in spite of these challenging times. And you can see some of our folks in their living rooms and their kitchens and their home offices sending commands, from their living rooms to Mars to help the rover continue to do its work on Mars. And in fact, you probably saw me also from my home office, and we've been here, but we're keeping things going. So we're very excited about that. Now, what's Curiosity all about? On slide 3, it gives you a bit of a primer about some of the really fundamental questions we ask about Mars, not just with Curiosity, but really with the entire Mars exploration program. One of the most fascinating things about Mars is that today it's a dry, cold desert, kind of like the picture shown at the right, which is a actual picture of Mars taken in the last few years. And you can see there's some wispy clouds in the atmosphere, but otherwise there's no water on the surface that you can see, and it's just a cold, barren, really a desert. But on the left, that's an artist's conception of what Mars may have looked like several billion years ago. There's really strong evidence that there were once lakes and streams and rivers, and possibly, as this artist has envisioned, maybe even an ocean that filled the northern hemisphere. We think all that occurred, if it did occur, about 3.8 billion years ago or older, in a period of time that geologists call the Noachian. Now, those words you see there, Noachian, Hesperian, Amazonian, are geologic eras or epochs, just like you would have on Earth in things like the Jurassic. So the Noachian is when we think Mars was the most wet, had the most liquid water, and it's controversial within the scientific community, but I happen to think Mars also was warm at that time because there was so much water and so much probably rainfall and water flowing in rivers going downhill into lakes that you probably had to have a warm enough climate to support that level of really a hydrological cycle. And then the Hesperian, that middle time period on Mars, something happened and the water started disappearing. And this is just about the time in the geologic record that Curiosity is exploring. So we're just in that middle time period. We're looking at rocks that date from that time period between when Mars was pretty reliably, we think from the evidence, wet, to the time after that where it is very dry. So one of the things we like to ask with Mars exploration is, Mars was once wet. Was it also warm? What's the evidence of that? And a very fundamental to Curiosity in particular is, was Mars habitable? Did Mars ever have conditions that could have supported life? So Curiosity isn't designed to actually look for signs of life, but taking kind of one step back, can Curiosity, with its instruments, determine if all the conditions were there on Mars to be able to support life? And if so, how long do they last? So what are those conditions that are required for habitability? And that's shown on slide 4, where, very briefly, we can think about what are kind of the key things that it takes to make somewhere on Earth livable, habitable. And we know from all forms of life that we've ever found that liquid water is something that's required for life as we know it. And persistent liquid water is even better because you want something to survive and thrive and not just, live for a day. Another thing that you need are the chemical ingredients of life. So all of our cells and all the material that makes up all living creatures that we found requires a lot of commonality in the chemistry. Carbon, for example, most of our, carbon's a very prominent element in all of our cells. All of our living tissues and functionality of life requires carbon-based molecules. So we looked for that. Did Mars have native supplies of carbon that life could have used and used as building blocks, along with things like nitrogen and oxygen and sulfur and phosphorus and hydrogen and all those other things that are very common to a lot of our cells. And then there's energy. Life needs energy to live and to multiply and to thrive. And so, on Earth, we have sunlight, of course. We have, we're at the top of the food chain as humans, so we can derive energy from eating other living things, plants, animals. But on Mars, if life ever existed, it probably was very simple, multi-celled organisms. And so you can, of course, have sunlight. Mars had sunlight, but, on Earth, you can dig down 2 miles deep and find living things on Earth that actually can draw energy from their environment, even 2 miles below the Earth. They can draw energy from the chemistry of rocks around them. And so that's another source of energy that we can look for on Mars. Does Mars have those same kinds of energy sources that life uses on Earth? So that's what Curiosity is all about, and what we're looking for are those elements of habitability. And we do that with a rover that has a lot of different scientific instruments on it, as shown in slide 5. So as many NASA spacecraft are, you have a platform, a spacecraft that allows you to have some kind of ability to access something whether you're flying by a planet or landing on it, or in this case, driving around it. And on that platform, you bolt on a lot of scientific experiments. So with Curiosity, that platform is a car. We thought it was important to assess habitability at multiple sites, not just in one landing site. So we needed something that could drive around. And then upon that vehicle, we have 10 different scientific instruments that are all labeled in this diagram that do a lot of different things. They, of course, have cameras that provide our vision and our ability to see different colors. We have laboratories that are what makes the rover so big. So in the front end of the rover are these laboratories called SAM and CHEMIN that look at the mineralogy and the chemistry of samples. And then, of course, we have this 6-foot robotic arm. And that is the purpose of that is to hold a drill so that we can drill into rocks and deliver samples to the SAM and Chemin laboratories. There's also a whole bunch of other instruments too, which I won't go into now, but it takes a village of instruments to be able to do the kind of science that we need to do with Curiosity. We also need a good landing site. So on slide 6, this gives you an idea of the area that Curiosity has been exploring and why we decided to send Curiosity here. So in the lower left, you can see that we went to a big impact crater, this round depression on Mars' surface caused by an ancient asteroid or meteor impact. And it's about 100 miles across. But what's really unique about this particular crater is that it has a mountain in it. And that mountain isn't just the mountain that sometimes forms when a crater forms and the middle of the crater rebounds up. This is actually a mountain of layered rock that must have been brought inside that crater by either wind or water. And the fact that it has layers and the fact that those layers change in composition as you go higher and higher on the mountain, as shown on the right there, where you have some layers that have this iron oxide called hematite. You have other layers that have a lot of clays in them, and you have other layers that have sulfates. We can see all this from orbit. And so that made us get pretty excited about sending Curiosity there because, one, all that layered sediment must have been brought in by wind or water, and water is a possibility. And two, all those different variations in the composition of the layers means that as those layers were being built up, the environment was changing. You went from environmental conditions, maybe the temperature or the amount of water in the environment. In some times, you would form hematite, this iron oxide. In other times, you would form clay, which is like soil on Earth. It means that a lot of water has interacted with the rock and broken down the rock and turned it into clay. And then finally, near the top of what's shown in this picture, you have conditions that would form sulfates. And sulfates are you can think of them as like salts. It might mean that the water was there, but then was evaporating quickly and Mars was drying out, leaving those sulfates behind. So this just looked like a great place to send a car to drive up the mountain and be able to ask those questions about habitability, to look for water, to look for the chemical building blocks of life and energy sources at each one of these time periods represented by these different mineralogies and different environments on the mountain. So that's what we did. And we got there and we've been driving up the mountain for now 8 years. And one thing that we found that's been very persistent is what's shown in slide 7, which is that, now we're looking kind of close up at rocks that make up the mountain itself. And you can see that these rocks are very finely layered and the layers are quite horizontal. And so each one of those layers is only 1 or 2 millimeters thick. But now we've studied over 1,200 vertical feet of bedrock, so nearly a quarter mile from top to bottom vertically. And almost all of it has been made up of these millimeter scale layers of very fine-grained rock. And so what this is telling us, really by our best analogies with where you'd find similar sediments on Earth, is that these kind of sediments, this fine-grained rock, sediments that are millimeters thick and very flat and horizontal are what happens when you have a lake that is being fed by a very silty or muddy stream, and then slowly that silt gets in the lake and just gradually settles down over the floor of that lake, leaving a thin layer of this very fine-grained sediment. And that happens year after year after year as the seasons change or the climate changes, and you form layer after layer. So after a pretty, now thorough geologic study of this mountain, Mount Sharp, we think that most of it formed as mud from the bottom of an ancient lake that once filled a part of the floor of the crater and then kept rising up as more and more mud covered the bottom of that lake. So this meant that water was in this crater for a long time, and also that there was quite a lot of water. Well, that was the story for several years. And as we've gotten higher and higher on the mountain, we're starting to see signs that actually things have begun to change in terms of the ancient climate. And so the next slide, slide 8. This was a pretty fascinating discovery. One day we saw what looked otherwise like a typical rock on Mount Sharp. A lot of it's been broken down, so we often see pieces like this. But this one had a really interesting texture on the surface. And as we studied that texture and looked through all the things that we know about geology on Earth and what would form that kind of pattern on a rock, the best thing we could determine was that these are mud cracks. These are cracks that form when a layer of mud, like I described, settling out from a lake, is suddenly exposed to sunlight, like maybe the lake dried up, shrank, and the shoreline was exposed. And that mud that once was covered by water was now exposed to the sun, dried up, and formed these little cracks as it desiccated. And so, what kind of blows my mind about this particular picture is these kind of cracks would form just in the span of a couple days. So you're looking at something that happened over a couple days, 3 billion years ago. So it's really fascinating to think that we can see something like that preserved for us to study today. But in the bigger picture sense, this tells us that those lakes were not there forever, and this probably represents a time when the climate was changing, but the lakes were present, but they were maybe shrinking in the summers or shrinking as the climate changed year to year, and then maybe coming back later. So things are getting a little more intermittent. Well, at some point, the lakes completely disappeared, and all that, what used to be mud, turned into rock. But from slide 9, we can see that things actually happened even after the lakes disappeared and all that mud turned into rock. And what we see are that when that rock cracked, more water, groundwater, flowed through those cracks, and it had minerals dissolved in it. And as the groundwater flowed through those cracks, it precipitated out minerals in those cracks. And what we're left with today are these veins, these little fins of mineral material, in this case calcium sulfate, that used to line cracks between the rocks, but now the rock has been eroded away, and you're kind of left with the vein, the fin, sticking out. This is not too different from a hard water deposit in your faucet, or maybe a stalagmite in a cave somewhere. Same type of thing. You have groundwater that's rich in minerals, and it's precipitating out the minerals when it on surfaces, like the insides of these cracks. So again, with the big picture, now we know that Mars had water in these lakes for long periods of time. And those lakes lasted a long time. Then they disappeared. But even long after they disappeared, still more water was there in the environment, flowing as groundwater beneath the surface. And that is what tells us that time scale that Mars was habitable is even greater than just the time period that lakes were there, but it also extended well beyond that. Next one, on slide 10, well, we've talked a lot about water and the persistence of water. What about those building blocks of life? So we also are able to look for organic molecules, these carbon-containing molecules, by delivering the material to our laboratories. And we've been able to find simple carbon-containing molecules. We haven't hit the home run yet and found like an amino acid or something like a DNA, that would really get us all Nobel Prizes. But what we have found are simple organic molecules that are native to Mars. So these form naturally on Mars and are building blocks that life could use or could have used if it ever was present. Interestingly, the ones that we seem to find a lot in Gale Crater, where Curiosity is, are ones that contain sulfur. So you can see that molecule in the picture has a bunch of carbons and a yellow sulfur molecule bonding them together. And we know from Earth, from basically just even technology, like how you make a strong tire for your car, is that you can use sulfur to strengthen organic molecules or organic materials like rubber. And so the same thing happens down at the molecular level. Sulfur-bearing carbon molecules are stronger than other carbon molecules. And those are the ones we're finding today, which leads us to conclude that the sulfur strengthening them is what has allowed them to survive over 3 billion years from when they were first created in that ancient lake environment to be able to find today. And a lot of the other carbon molecules have been degraded over time, leaving these strong ones to survive. So that's pretty fascinating. And why is that interesting for us? Is because, we're still trying to look for evidence of ancient life on Mars. And this gives us an idea of what kind of evidence might be preserved for us. It's, we have an idea that some things are being retained, and that's a very promising missions that are going to actually try to return samples to look for life on the Earth. So next, I just a little on slide 11 about our where we're going in the future. So you can see this map of the lower part of Mount Sharp, which is Rover, and we've climbed through area on the path, and we're now where it says current location, and ahead of us, we're going to climb to the sulfate unit. But right now, as you can see, when it changes to the colored version of the map, you can see we're in an area called the clay unit to the south of us, or actually to the north of us, and just to the south of us is a big feature called the green hue pediment. And we're going to talk about both of those things in the following slides. So first, where we are now, on one side of us is the clay unit on slide 12. We've been looking forward to getting to the clay unit for a long time because, as I mentioned earlier, the clay unit is, we can tell from orbit, even from the satellites we have at Mars in orbit, that there's a lot of clay here. And clay means that a lot of water was there interacting with the rock. And it also is a good place to find those organic molecules that we're after because they get trapped inside clay molecules and preserved for us over time. So we got here about a year ago, and we've been exploring this area, and we have been able to verify with the rover's own instruments that it is very rich in clay. It's in fact 30% of the rock has been turned into clay minerals from what it used to be, more pristine volcanic rock. And it's the most clay we've ever seen in rocks. So this truly is the clay-bearing unit of Mount Sharp. And we've also been able to determine that it's not something that is a fluke. It's actually part of Mount Sharp. It didn't form later. It wasn't brought there by something else. It is a strata that goes through Mount Sharp and was deposited in lakes just like all the strata below it. So that's another big conclusion for us to be able to put it into the timeline of Mount Sharp and know that it's not something that was just added on later by a landslide or something like that. And finally, we've been able to look for organics, and we've found, again, a lot of those sulfur-bearing organics. And importantly, for the first time, we were able to find higher molecular weight organics. So not just those simple ones, but slightly longer ones. So we found molecules that have 10 carbon atoms in them or 12 carbon atoms in them. They're still maybe short compared to those really advanced carbon molecules that are in our cells, but it ain't nothing. It's more than just those very simple ones. And the 10 to 12 carbons is getting us to the point where it's getting pretty interesting in terms of biology being able to use them. And the green hue pediment. Let's talk about that on slide 13. So what's that about? Actually, if you'll go back to slide 12, there's a good picture of it there. Above the clay unit, you can see that there's this cliff that's very horizontal, where the arrow is pointing, green hue pediment. And that is a shelf of material that's just about 6 feet thick, made out of sandstone that just cuts across the clay-bearing rocks. And from far away, and it looked very, it's quite a big feature, and we were really not sure what it meant. And so we were looking forward to getting there and trying to figure it out. And now if you go to slide 13, you can see that we're up close to it now. And you can see those rocks, those orange rocks of the clay-bearing unit at the bottom. And then right at the top in the middle there, you can see that 6 foot thick sandstone, what we call a capping unit, just kind of the top of a butte there that that is the green hue pediment itself. We also have been able to determine that that pediment surface, that capping unit of sandstone, is not actually part of the flat strata that go all the way through the mountain that formed with the mountain. It actually was put on later by a different process. So it's not part of that continuous time record that is made up of Mount Sharp, but Mount Sharp was built up completely, and then later on, a big sand dune came across the mountain and covered a lot of those layers. And then that sand dune turned into rock and left this sheet of that 6-foot thick layer. So that's interesting geologically because we know that it's not continuous in time. It's also interesting because that sandstone sheet only became solid rock because water was interacting with it. If a dry sand dune had come across and never interacted with water, the dry sand would have just kept on going and blown away. But the fact that it turned into a sheet of rock meant that there was some water in that environment. So now we have yet a third era of time, the time when the lakes were there, the time when the groundwater was flowing, making those fractures filled with mineral veins. And then after all that, another era of water that helped cement that sandstone, that dune field into sandstone. And so water was present in this area for a long time. And it's been really fun to try to figure out all the different ways it was there and how the climate changed over time to allow that. So slide 14, this is just our gallery, our photo gallery of all our precious drill holes. Every one has a story behind them and required a lot of effort. So this is, we're very proud of this picture. Another thing that's pretty cool about this is all the different colors, at least variations between red, orange, and gray. And that tells you something really important from the chemistry standpoint, is that the gray samples, well, let me start with the red ones. Red, we all know Mars is red. And it turns out that Mars is red at the surface because oxygen in the atmosphere and in the environment has been interacting with the surface and oxidizing it, turning it red, kind of like rusting it. But Curiosity has found that, you can just drill a couple inches down and the insides of the rocks are still gray. They're unoxidized. And in some cases, not all cases, as you see here. And when the insides of the rocks are unoxidized, that actually is good for finding and retaining evidence of stuff from 3 billion years ago. So if there ever was life, and if there ever were complex organisms that we could now, in a sample that we bring back to Earth, we can maybe find some ancient DNA or something. The fact that we could bring back an unoxidized rock is a really good thing, because it means that the oxidation wouldn't destroy those that evidence of the ancient organic molecules that we're trying to study. So we're learning a lot, not only about Gale Crater, but about how future missions can take advantage of everything we're learning to improve our chances of finding life on Mars. So to summarize, from Curiosity's perspective, those pictures I showed at the beginning on slide 15 here, Mars was once wet. Was it warm? I think maybe you'll understand now why I personally am on the camp of yes, I think it was warm, because we have a quarter-mile thick of sediment that was deposited in lakes. That probably means that lakes were there for millions of years or longer. And a big lake with a lot of mud coming in from streams that flowed down the side of Gale Crater probably meant that there was a large body of water somewhere, another lake, maybe an ocean with evaporation happening, rain clouds coming over and dumping the water over Gale Crater, filling those streams up with water, causing the erosion and the silt to come in. And that happened for millions of years. And so it's hard to do that. There's ways to have some water moving around even in a frozen environment. Like there's a little liquid water even in Antarctica today, but it's a lot easier to do it if Mars was a little warmer and you could have more like a full hydrological cycle like on Earth today. Was it habitable? And for how long? Well, the lakes were there for tens of millions of years, and we found carbon molecules and other elements that life needs in a lot of those lake sediments. So, and the energy sources were there as well, whether sunlight or those chemical sources of energy. So we think that overall, the story is that Mars, at least at the Gale crater location, was habitable for tens of millions of years and maybe even longer. So that is a really wonderful conclusion from the mission. It's what we set out to find. And fortunately, the answer has been yes, which is the more exciting answer than if we had said no. So it's all good. And it really sets us up really well for the next mission on slide 16. And maybe I'm sure you'll learn a lot about this if you haven't already, because it's going to be in the news for the next year and more. So the Perseverance rover, which is the follow-on mission to Curiosity, not only seeks signs of past habitability like Curiosity does, but goes one step further with more advanced instrumentation on the rover to actually search for signs of ancient life. So Curiosity has really teed up the ball for this one, and we're really excited to see if Perseverance comes through and actually makes that detection of ancient Martian life. If it can't do it while it's on Mars, the proposed plan for now is to collect samples for eventual return to Earth one day, so that we can use the best laboratories on Earth to study the samples that Perseverance collects and make that discovery. So it's an exciting time, and I hope you all, stay tuned and follow along, and I'd be happy to answer any questions.
Great. Thanks, Ashwin. I always enjoy your updates because I always learn something new, even though I try to read everything I possibly can about the mission. We do have a bunch of questions for you. We'll get through as many as we can. The first one I'm actually going to take myself because it is a question that says, is there a project dealing with Mars that high school students could participate in by analyzing pictures or other data from the current spacecraft? The answer is yes. If you do an internet search for NASA citizen science, you will end up on a solarsystem.nasa.gov website, and scroll to the bottom. There is one NASA citizen science project for anyone, and that deals with Mars, and there's a whole bunch with other missions. And then there's another one that's in work and should be showing up on that website in the next couple of months or so. So keep an eye out for those. Next question for you, Ashwin. What evidence do scientists who believe that Mars was never warm point to, and how would they explain something like a lake?
Yeah, no, I appreciate the question. So what I didn't mention earlier is that for many years, especially since the time I was a student and the last couple decades I've been doing Mars science, is that everyone just kind of assumed Mars was warm. It had to have been if there's all this evidence for water. What's caused the tide to turn a little bit is the fact that with just like on Earth, we have a lot of models that are used, computer models that are used to try to simulate the climate and to understand why, like how it was warm, what was different about the climate 3 billion years ago that allowed it to be warm. And for Mars, we're unable to figure out how to make a model to make Mars warm 3 billion years ago. And so it's been really mysterious. We have all this geologic evidence of rivers and oceans and as lakes, as I described, but so far we don't understand exactly how the atmosphere was different to be able to support it. We think the atmosphere was thicker, and for many years that was the answer. If you would have asked me 10 years ago, I would have just said, well, the atmosphere is thicker, end of story. But more research has shown that if the atmosphere gets too thick, it actually starts condensing into clouds. The atmosphere itself, the carbon dioxide of the atmosphere itself, makes its own clouds and prevents it from getting any warmer. And so there's been other ideas of maybe adding other greenhouse gases, but that's the issue. So it's not that people don't believe in the lakes or the oceans or things like that. It's that some people just think we really have tried our best with these climate models and we can't figure it out. So perhaps that's telling us that Mars never was warm. Now, how would they explain the lakes? Well, even in a relatively cold Mars, where you're right around the freezing temperature, perhaps, you would have areas that are very icy. It's sort of like Antarctica. But underneath that ice cover, you might have a liquid water lake that's sort of insulated by the ice above it. And you can create lakes that way. You can even create mud gathering at the bottom of those lakes because you might have a stream underneath the ice. but everything is very slow in those very cold environments. Erosion is very slow, evaporation and precipitation are very slow. And so that's where I still feel like in that kind of icy environment, how do you form, a quarter mile thick of those deposits and create all that erosion to supply all that mud into Gale Crater? So sorry for the long answer, but it's a big mystery.
Yeah, that's a great answer. I appreciate that. Our next question is also about water. How does water just form on a planet? Is it random chemistry?
Yeah, it can happen different ways. There was water in the initial solar system when all the planets were forming. And so Jupiter, for example, has a lot of water in its atmosphere just from that way it originally formed. Earth and Mars, we think, had that water, but then the sun was very active, and Earth and Mars both lost a lot of that initial water. But then it was resupplied, for example, by comets that were still a lot more populous back then. Comets were flying around and hitting Earth and Mars, and enough comets could hit those planets to actually supply them with a lot of water that was then retained and not lost again. So it's ways like that, and water also comes out through volcanoes and can then be part of the environment.
Okay, very good. Next question is about life. As Earth's glaciers are receding, we are finding bacterial life. Do you expect that as a possibility on Mars, at the poles, or anywhere else?
Yeah, it's interesting. If you were to have any, well, um, there are a lot of people who think that if we could just do whatever we wanted, and money and technology were not an object for Mars, the best place to look for life would probably be underground, because we know that Mars had 3 billion years ago might have had a nice atmosphere and a little bit more protection from the ultraviolet light of the sun and all those things. And today, the surface environment is actually pretty harsh for life. So if you're going to try to look for things that are alive today, maybe you'd want to dig underground, because maybe there's still liquid water underground. You're protected from that harsh surface environment. So I think that's kind of along the lines of what you're saying. If there are places that are naturally being exposed that were once underground to being now at the ground level because ice has receded, or maybe a landslide's happened, or an impact crater plows the surface, maybe that's a cool place to look.
All right, very good. Next question is looking toward the future. What are the plans for the Artemis mission to use data from the Curiosity or Perseverance rovers?
Yeah, I can speak to a couple of things. I think a lot of those plans are still being worked out, exactly how they'll use or what they'll do at Mars, because a lot of the focus is on the moon right now, of course. But both Curiosity and Perseverance have parts of the mission that are actually flown on behalf of the human space program of NASA. And so Curiosity has an instrument called RAD, the Radiation Assessment Detector, which measures radiation at the surface of Mars, which we've never done before. So we know that radiation in space can be harmful to astronauts, so you have to protect them from that radiation. And so we've measured it. We measure it in the space station. We measure it all the time with satellites. But on the surface of Mars, Mars' atmosphere is thin, that radiation still gets in. And it actually gets changed by the atmosphere, in some ways for good, in some ways for bad. So measuring radiation from the surface of Mars is really important to helping us learn how to protect astronauts who will one day go to Mars. For Perseverance, they're tackling a different issue: is how do you supply oxygen to astronauts and to missions that bring astronauts. So there's two reasons you might want oxygen. One is to breathe, of course, and the other is to make fuel for your return trip home, for example. And so Perseverance carries a demonstration experiment where they're going to take CO2 from the atmosphere, carbon dioxide, and convert it into oxygen, and try that out and see how it works on Mars.
Cool. All right, one more water question. Did the water escape from our battery system, or is the water there in a different state?
It's a little of both. So right now, there's a lot of water on Mars. In fact, if you were to melt the polar caps, believe it estimate is that you something like 10 or 30 of water covering the entire planet. So that's a ton of water. It's just all on these polar caps. Um, but even more water that now escaped. And it escaped. So all this water being lost, the climate change is complicated. But another element is the fact that Mars had a magnetic field. And once that magnetic field was lost, as Mars cooled down more quickly than it did, then the solar wind particles that are always streaming, Mars no longer had defense against that. The magnetic field shield Mars against that. But when that shield went away, those particles would come in and grow the atmosphere and get rid of that water. And so that's how we think the water was lost and the entire atmosphere, thicker atmosphere, was lost originally.
Okay, that makes sense. Now, is there any carbon dating capability on Curiosity?
Yeah, we don't have carbon dating capability, but we do have rock dating capability. And that's at least a step towards that. So it would be, well, actually, I take that back. We probably could do carbon dating. We just haven't found anything that was living recently enough to do the kind of carbon-14 dating that we do on Earth, which is a time scale of thousands of years or something. So what we have been able to do on Mars with our instruments is use other radioactive isotopes in rocks that decay over time scales of millions of years or hundreds of millions of years. Things like argon. So we can measure argon of two different types, just like you would measure carbon-12 or carbon-14 for the carbon dating. We can look at different kinds of argon, 38, 40, that sort of thing, and figure out, and actually argon turning into its daughter product. So anyway, to make a long story short, we've been able to date rocks and figure out how old they are at a kind of a rudimentary level. We weren't designed to do that, but we found ways of estimating it.
All right, very good. And not sure if this one's in your field or not, but could you talk a little bit about the image processing and data analytics that are related to the work that we're doing on Mars?
Yeah, I mean, that's a pretty broad question, but most of it, I guess I'll just say that most of it happens on the ground. So like many space missions, they take a few, several years to develop. And because you're sending them into space where you can never repair them, you end up using pretty reliable older technology when you send them. So, we're in the days now when you have a 20 megapixel camera on your phone, and Curiosity was designed, 15 years ago, and it probably used 10-year-old technology 15 years ago. So we have something like a 1 megapixel camera on the rover. So, and same with the computer. It's nothing to brag about other than the fact that it's awesome and it works, But once the data come to Earth, the neat thing is that Earth technology can continually be improved. And you can use new ways of processing the data. And so now we can, visualize our data in, we use the virtual reality goggles to have our scientists actually walk across Mars on the terrain. And that's something we never dreamed of 10 years ago when we built the rover. But we can use that same data from the rover in just different ways, different processing ways to visualize it better, to extract more data from it.
Very good. I have one last question for you, and this one is a question that I know a lot of kids ask and teachers will be very interested in. What inspired you to become a JPL scientist?
Yeah, I think it's an answer that you'll hear pretty commonly around my colleagues, which is that sense of exploration. So the idea that you can go places, even virtually, that no one's been before, and you can discover things that have not yet been discovered. And for me in particular, it was actually it was actually planets, and robots were just fine. When I was 8 or 10 years old, I just remember seeing pictures of the surface of Mars from the Viking landers, and pictures of the surface of Venus, for example, from the Russian landers. And what struck me about those is that unlike other pictures from space, they were taken like at eye level, like you were just on the planet. and you could look across the surface and you could see, like on Mars especially, you could see hills off in the distance and rocks on the ground that you feel like you could just walk right into that scene. I think that's when I really decided I loved the idea of exploring these planets. And now I get to, drive a rover every day around the next corner and see what's there, and actually, make pretty important discoveries about the nature of life in the solar system while we're at it. So that's what inspired me.
Very cool. Well, thank you, Ashwin. I really appreciate your time. I know you're a really busy guy, and I appreciate your presentation and answering all of these questions. So we're going to make a transition now into some educational products. And for those of you who asked questions about the Perseverance rover, I have held on to those questions. I want you to come back and ask those of our Perseverance guests in the coming weeks. So we'll be sending out an advertisement for that soon. But thanks again, Ashwin. Appreciate your time.
Thank you, everybody. Bye.
Okay, so we're going to go ahead and take a look at my first slide. Many of you are aware of the NASA JPL education resources. We have some new things for you. So our most popular page is our Teach page, which contains lessons for teachers to use in the classroom, either the classroom in person or an online classroom, if that's what you're teaching in now. These can be searched by grade level, by topic, and they're all standards aligned. We align with the next generation science standards and the Common Core state standards for math. Now, the next slide it features one of my favorite activities. This Explore Mars with Scratch is a programming activity where students would have an opportunity to program a rover to drive around in a video game. So they make their own video game using Scratch. And if, as a teacher, you're not familiar with Scratch, that's okay. We have done screenshots of all the steps. We give you a step-by-step instruction on how to accomplish this. And all of the screenshots are there for all of the icons and such in Scratch. Now, on my next slide, we have the student version of this. And this is kind of what we're trying to do as a new thing. We're trying to make student versions that are companion pieces to our teacher lessons. So Make a Moon Mars Rover game is what you might give to a student, and they program the Mars rover as you would have described in the lesson, and we give the steps without the pictures of how to do it exactly. So we give hints and tips, and it's kind of like a challenge. The next slide that we have come up with as a call to answer the call to online learning is called Learning Space with NASA at Home. The NASA is doing a big push to try to get all the resources that teachers and parents can use at home in schooling their students. And our contribution has a lot of new things that you will see. The videos are the newest. We have the lessons that we used to have, but now we're putting videos with them. So short little introductory videos that are targeted for a student audience. And the next slide shows what you see if you scroll down the page a bit. If you want to look at lessons or activities for kids by grade level, you can click through the tabs. We have a variety of things. And the next slide is one of my favorites. It's Build a Rocket and More with Shapes. And you recognize that probably as tangrams. Now, the materials list shows that you need a template. Now, we know that most students don't have a printer at home. For those who do, they can download the template and print it out. For those who don't, we include some suggestions like turn up the brightness on your computer screen and get a blank sheet of paper and place it over the computer screen and trace the template. And then you can do the rest of the steps that are shown in pretty nice little picture illustrations here. And so hopefully that makes it more accessible for students who can find a piece of paper and some crayons or pencils, but they can't necessarily come up with a printer. And as I mentioned, next slide, this is the companion teacher page that you're probably familiar with if you know our resources, the Tangram Rocket. It has a bunch of background for teachers, and it has the standards, as I mentioned, listed. The next slide. Another video that is new that I really like is solar system size and distance. For those of you who have tried to teach the distance between the planets and the relative sizes of the planets, you know that it's really hard to make a model of both of those at the same time. It might be even harder to explain to kids why that's hard. So we made a little video that has an explanation of that, some animations, and also a lot of our videos that we're producing now, we are captioning in Spanish. So if you're on YouTube, you can go into settings and select Spanish captions. And hopefully that'll make it more accessible to some of our Spanish speaking families. And next slide, another one of my favorite recent activities is explore Earth and space with art. This is using the elements of art to study landforms on other planets and on Earth. So the first feature is on Earth, and there's a little quiz. Students do some little bit of reading, and then they take a quiz, and they can find out how well they did, take the quiz again. And coming soon, very soon, we're going to have the second version of this, which is Explore Mars with Art. And it's going to be kind of the same thing, except the images, instead of being from Earth features, are going to be Mars features. So hopefully that will give you some resources to use in the classroom. I hope that you guys will give us some feedback on how this session went. Well, if you registered, we're going to send you a little reminder and a little survey later. But we have upcoming 3 sessions on the Perseverance launch. So the Mars Perseverance rover is launching in mid-July. And next week, we're going to kick off at this very same time. We're going to kick off the Perseverance Mars Rover Educator Conference. It'll be a 1-hour feature, just like this was today. Someone different will be the speaker, and we'll be featuring different educational activities. So with that, I hope that you will enjoy your afternoon and join us for the future. Thanks.